You deploy a new agentic AI workflow on your local machine, and, well, it's just flawless. It follows every formatting rule, it respects your linting constraints, and it writes perfect code.
Right, it feels like magic at first.
Yeah, exactly. But then you hand the repository over to a teammate, they spin up Claude on their machine, and suddenly the agent is completely ignoring all your security
Oh
protocols.
yeah, I've seen that happen so many times.
Or maybe you're using it yourself, right? You've been exploring this massive monolithic code base for 2 hours, and right when you need it to implement a specific custom class, it just hallucinates generic framework boilerplate that has nothing to do with your system.
Right, and that is exactly the moment when engineers realize they aren't just debugging software anymore. You are suddenly debugging context windows, scoping boundaries, and configuration hierarchies.
It's a completely different skill set.
It really is. I mean, when an agent behaves unpredictably, it almost never means the underlying model is broken. It usually means the system architecture feeding that model has a leak somewhere.
So, that structural perspective is exactly our focus for today's deep dive. We are taking a highly technical, architect-level look at Scenario 2 of the official Anthropic exam guide, which is all about code generation with Claude Code.
When we really need to emphasize something here, the examguide.md file is the absolute and definitive guide sourced directly from Anthropic.
Right, it's the ultimate source of truth.
Exactly. We are treating that exam guide as the definitive survival manual for building DevOps-grade agentic workflows. Because, relying on clever prompt engineering simply will not scale when you have a team of developers interacting with hundreds of thousands of lines of code.
It definitely won't. I mean, if you treat an AI agent like a basic chatbot where you just type instructions into a prompt every single time, you're just wasting tokens. You're begging for inconsistency.
Yeah, to scale an agent, you have to define where your rules live, how those rules cascade across directories, and how to preserve the agent's working memory.
So let's start with the rules of the road. Before an agent writes a single line of code, coding standards and security guidelines have to be established as passive rules, right?
Right, they need to be there in the background.
But the challenge is ensuring those rules load reliably for every single engineer. The exam guide points out that misunderstanding the CLAUDE.md configuration hierarchy is the main cause of those works on my machine discrepancies.
Yeah, so the cascading loading order is strictly enforced by the architecture. It basically operates across three main levels. You've got user level, project level, and directory level.
Okay, so let's look at that exact diagnostic scenario we mentioned at the start. A senior developer writes out detailed security guidelines, but when a new team member clones the repo, Claude just ignores them.
Right, so what's your first instinct as an engineer when a new developer clones a repo and a config file is missing?
I mean, I'm checking version control immediately. If the file isn't in Git, it must be living entirely in a local, unshared directory on that senior developer's machine.
Exactly, and that points directly to the user level configuration. The senior developer put those critical rules in their local home directory, so the ~claude/keyLED.md file. Ah, I see. So the user level file is just a personal configuration space. It's never actually committed to the repository.
Right. Structurally, those security rules simply did not exist in the new teammate's environment. To fix it, you have to elevate those standards to the project level.
So they need to live either in the root of the repository as a standard CLAUDE.md file or tucked inside a .claude directory at the root so Git can actually track them.
Yeah, getting them version controlled is step one. But that introduces a secondary architectural problem, especially in massive monoredos.
Oh, because of all the different languages and frameworks mixed together.
Exactly. Imagine a single repo with Python backend, a TypeScript frontend, Go microservices, and Terraform files. If you dump all the rules for every single language into one root CLAUDE.md file, you get a massive unreadable document. And it floods the context window, right? If I ask Claude to update a Terraform file to modify an AWS security group, there is absolutely no reason the AI needs to be reading through 50 lines of Python linting rules.
Right. Loading irrelevant rules just wastes your context budget and actively risks confusing the model. So the architecture gives us two ways to prevent that rule bleed.
Okay, what's the first one?
The simpler approach is modularity, using the add import syntax. Your root file stays clean by just importing separate, specialized markdown files. But the real power tool for conditional scoping is using the .claude/rules directory combined with YAML front matter.
Oh, I want to break down the mechanics of that conditional scoping, specifically how we use glob patterns. So for anyone listening who hasn't configured these recently, a glob pattern is essentially a wildcard string used for dynamic matching.
Yeah, you're basically using asterisks to target file types, no matter how deeply they are nested in the folders.
Right, so inside the rules directory, you create a focused file, let's call it terraform.md, and at the top, you put a YAML front matter block with a paths field.
Exactly. And if you define that path using a glob pattern like infra slash asterisk asterisk slash asterisk, you create a strict loading condition.
So the YAML front matter acts like a bouncer at a club door. Claude checks the file you're currently editing. If it's inside the infra directory, the bouncer lets the Terraform roles into the VIP context window.
I love that analogy, yes.
But if you switch to editing a Python file in some completely different folder, the conditional match fails, and those Terraform rules are structurally blocked from loading.
The bouncer analogy is perfect because it guarantees that specific rules only consume tokens when they are actually relevant. The exam guide specifically highlights testing conventions to show why this global wildcard approach is so necessary.
Well, that raises an interesting design question for me. If I have React test files in my front-end directory, why wouldn't I just drop a directory-level CLE.md file straight into that specific folder? Wouldn't that achieve the same conditional loading without needing glob pattern?
I mean, a directory-level file works fine if your architecture strictly quarantines all tests into one single flat folder. But, modern component-based code bases almost never do that.
That's true. You usually find button.test.tsx sitting right next to button.tsx inside deeply nested UI folders all over the place.
Exactly. So relying on directory-level files would mean copy-pasting the same testing standard into dozens of individual component folders. It's completely unmaintainable.
Right. So by placing one single file in the rules directory and setting the path to match asterisk slash asterisk dot test dot tsx, the agent dynamically intercepts any test file anywhere in the repo.
Yep, it injects the testing conventions automatically. It's just a highly efficient way to manage cross-cutting concerns.
Okay, so we've secured the baseline passive rules, but a DevOps engineer doesn't just write text, right? They execute multi-step migrations, they deploy infrastructure. Passive rules can't govern a multi-step action.
Right. For that, you have to transition into active workflows using commands and skills. And they share a similar scoping hierarchy to the rules we just talked about.
So custom/commands in the .claude/commands directory are version controlled for the team, while commands in the home directory are personal.
Exactly. But to unlock true autonomous workflows, you use skills. Those live in the .claude/skills directory and are defined by a skill.md file.
And the behavior of those skills is heavily dictated by their YAML front matter, which sets the runtime boundaries. The exam guide focuses heavily on argument hint, allowed tools, and context fork. Let's look at argument hint first.
Yeah, the argument hint field essentially acts as a safety pause.
So if an engineer runs a /migration skill but forgets to pass a required name, the agent won't just guess.
Right, it pauses and actively prompts the user for the missing parameter before doing anything. It ensures deterministic execution. But honestly, the far more critical boundary is allowed tools.
Oh, for sure. When you give an AI agent access to your local machine, you're letting it read files, run bash commands, execute scripts. It's a huge risk.
It is. I mean, if you build a custom skill to generate boilerplate code for a new database model, the absolute last thing you want is the agent hallucinating a cleanup step and dropping a table using a shell tool.
Yeah, that would be a nightmare. So allowed tools mitigates that threat model.
Exactly. By explicitly declaring which tools a skill can access in the front matter, you establish a hard security perimeter. For a code generation skill, you just restrict it entirely to file read and file write operations.
So even if the model tries to generate a destructive shell command, the system architecture just blocks the execution because the bash tool isn't provisioned for that session.
Right, the system just says no. But while security boundaries are vital, if we're talking about the actual quality of the output, we really have to look at the context fork setting.
Yeah, the syllabus positions context fork as arguably the most critical setting for deep code base exploration. Why is that?
Well, without it, complex skills degrade the performance of the agent almost immediately. Think about it. When an agent maps out a legacy microservice, it has to navigate a lot of unknowns.
Right, it's going to use the grep tool to search for variable names, use bash to run find commands, and read a bunch of files that turn out to be dead ends.
Exactly. And if the skill isn't running in an isolated subprocess, The agent is just dumping every raw search result, every error message, and hundreds of lines of terminal output straight into your primary conversation history.
Oh, wow. So all that raw terminal vomit just dumps straight into the main chat.
Yes, and it causes immediate token pollution. The main contest window just fills up with the noise of discovery. The model's attention mechanism gets stretched across thousands of irrelevant tokens, and it completely loses focus on your actual prompt.
So setting context to fork essentially spins up a soundproof room. A subagent goes into that isolated space, makes a massive mess running grep commands, reasons through the architecture, and then what? It just leaves the mess behind.
Exactly. It exits the room and hands the main session a perfectly formatted, concise summary. Your primary conversation history never even sees the terminal vomit.
That is incredibly powerful. But, designing these team skills introduces a pretty inevitable structural conflict. DevOps teams mandate standard workflows, but individual developers always want to customize their local environments.
Right. People love their personal scripts.
So what happens when a personal workflow collides with a team mandate? Who wins?
The exam guide categorizes this as the precedence trap. If you have shared team skills in the project directory and personal skills in your local home directory, there has to be a hierarchy to resolve naming collisions.
Okay, so let's say the team enforces a /commit skill in the shared repo. It runs project-specific linting and formats the commit message to a strict company standard.
But locally, you prefer your commits to automatically run a personal spell check script you wrote. So you create your own skill named /commit in your personal home directory.
Wait, if I do that, is there some override equals true flag I need to set in the YAML front matter to make it work?
No, there's no flag at all. It relies entirely on the structural hierarchy. Because your custom skill is in your personal directory and shares the exact same name as the project skill, your local system silently overwrites the team's version.
Wait, really? So as a DevOps engineer, I can hijack the team's /commit command just for myself and nobody else is affected?
Yep. The local personal environment always takes absolute precedence. When you run /commit, your machine executes your customized version. The rest of your team continues using the mandated project version, and the core repo remains untouched.
That's a great feature for deep local customization. But from a diagnostic standpoint, if a developer opens a ticket saying the new team command isn't working for them, the very first thing I should check is a naming collision in their local home directory.
Exactly. Understanding that precedence trap will save you hours of debugging. But, even with perfect configuration, isolated skills, and correct precedence, we eventually hit the physical limits of the technology.
Right. If you're running an agent for hours, navigating across modules and generating code, the context window is going to inevitably reach capacity.
Which brings us to Domain 5 of the syllabus, context management and reliability. To manage memory, you first need visibility into what the model is currently holding.
And that's where the /memory command comes in. It acts kind of like checking the active RAM on a server, outputting exactly which files, rules, and history turns are currently loaded.
Right. And if that RAM is getting full, the primary tool provided is the /compact command. It frees up space by compressing older conversation history into summaries.
But summarization inherently means losing precision, right?
Mm.
And that loss of precision leads directly to context degradation.
Yes, which is the exact symptom we discussed at the very beginning of this deep dive. Let's trace why that happens. In the first hour of exploration, Claude finds a highly specific, custom JWT validation class buried in your code, and it uses it perfectly.
But then 2 hours later, when I ask it to write a new endpoint, it completely forgets the custom class and just hallucinates generic authentication boilerplate.
Because the specific details of that custom class have been pushed so far back in the history or compressed by the compact command that they can't compete for the model's attention anymore.
So the generic framework patterns it learned during its initial pre-training just overpower the specific local facts it discovered earlier in the session.
Exactly.
Okay, so when engineers experience that degradation, the most common distractor answer, and I see this all the time, is to just go into the API settings and crank up the max_tokens parameter. I mean, the logic seems sound, right? If the agent is forgetting things, just give it a bigger memory limit.
I see that constantly, but it is a fundamental misunderstanding of the API architecture. Max tokens does not control the size of the model's memory or the context window.
Wait, it doesn't?
No, it is a strict cap on the length of the output the model is allowed to generate in a single response. Changing that parameter has absolutely zero effect on how much conversational history the model can ingest or retain.
Oh, wow. So if increasing API limits won't fix a failing memory, and internal compaction loses precision, we need a real architectural solution.
Right. If internal memory fails, the only logical step is to externalize it to persistent storage. And that is the ultimate fix for long-running workflows, the use of Scratchpad files.
Ah, Scratchpad files. So instead of hoping the agent remembers a specific variable from 50 conversational turns ago, the architecture explicitly forces the agent to export its state.
Exactly. You are effectively requiring the agent to write its own documentation before it loses its train of thought.
Yeah.
It creates a local markdown or JSON file on the disk and writes down the critical architectural details.
So it logs that authentication uses the custom JWT class, or that database queries must use a specific singleton pattern.
Yeah, because a file written to a disk is completely compression resistant. It doesn't fade over time.
All right.
So when you transition from a long discovery phase into an active implementation phase, you just provide a simple instruction. Read the Scratchpad file.
And the agent pulls those exact, precise, uncompressed facts directly back into its immediate, fresh context window. It bridges the gap across phase boundaries perfectly.
It offloads working memory into durable storage. It's brilliant.
So if we pull all of these architectural pieces together, for you listening, we've moved far beyond basic prompting. We established the baseline rules using the configuration cascade, avoiding scoping errors by ensuring team standards live at the project level, not the user level.
Right, and we controlled token bloat by using the rules directory and glob patterns, ensuring rules only load dynamically when their specific file types are active.
Then we transition into multi-step operations using isolated skills, leveraging allowed tools to prevent destructive shell commands, and context fork to ensure terminal output doesn't pollute the main window.
We also map the precedence trap, recognizing that personal skills structurally override team skills to allow for local customization.
And finally, we addressed the physical limits of the model. We acknowledge that max tokens cannot cure context degradation, and that the only reliable way to maintain precision across hours of work is to mandate external Scratchpad files to persist state.
When you apply these configurations strictly, you stop treating the AI as a fragile chatbot. You're defining the operational boundaries, the memory architecture, and the security perimeter for a synthetic teammate.
Which leaves us with a pretty compelling, forward-looking reality to consider. We are now architecting local environments where our IDEs trigger isolated, context-aware subagents. These subagents are searching repositories, respecting conditional rules, executing local shell commands, and writing their own external Scratchpad files to maintain memory over time.
It's a huge shift.
It really is. So the provocative thought I want to leave you with is this. At what point does the repository itself stop being merely a passive storage location for code and become the literal long-term hippocampus of an entirely autonomous digital developer?
That is the question. If the code base holds the agent's conditional rules, its active skills, and its externalized memory structures, the repository isn't just the product being built anymore. It functions as the mind of the worker building it.
Understanding the architecture that supports that mind is exactly what separates struggling with hallucinations from deploying truly reliable automation. Thank you for taking this deep dive with us today.